All right, so we're going to have a little online class here. Adjust this just a bit. All right, so the last thing we did in class is we identified or showed that we understand how to identify the relationship between the hydroxide ion concentration, which is shown right here for this example, the hydrogen ion concentration, and the pH. All right. So we talked in class, and we said that the hydrogen ion concentration. Let me find this pen here. We said that the hydroxide ion concentration times the hydrogen ion concentration equals 1 times 10 to the minus 14. All right, so let's see. There we go. Equals 1 times 10 to the minus 14. Okay? So, if we know that the hydroxide ion concentration equals 3.2 times 10 to the minus 3, then we can identify this by solving for that. All right? And to make sure that you guys understand how to do that in your calculator, I'll show you a little bit of how we do this, right? So we want to make sure that we, let's see, what's the best way to do this? All right, so it's kind of sideways calculator like this, but we're going to just show it to you one time, and then we will, hopefully you understand. But it's important that we know how to write our scientific notation values into our calculator appropriately. If you don't have this kind of calculator, then you're going to have to go and just type it into YouTube, how to write scientific notation on the calculator that you have. Okay? So, the math that we're going to perform here is this 1 times 10 to the minus 14 divided by 3.2 times 10 to the minus 3. So I go 1, and then times 10 to the is that combination. And then I say minus 14. All right. 1 times 10 to the minus 14. And then we're going to divide by 3.2 times 10 to the minus 3. So 3.2 times 10 to the minus 3. All right, and so that should be our 3.1 times 10 to the minus 12. Okay, so that's how we get our hydrogen ion concentration if we have the hydroxide ion concentration and vice versa. Okay, for pH, we take the negative log of the hydrogen ion concentration because P, negative log, right, H, hydrogen ion concentration. So I'm going to say negative log, and then I'm going to type in my 3.1 times 10 to the minus 12. Okay, and then I can just push enter. And so that will be my pH of 11.51. Okay? All right, so go through the rest of this slide and figure those out if you haven't done so already. If you have, just keep listening. You should push pause and finish all these up. Make sure you know how to do those in your calculator. Okay? All right, push pause. Are you done? Great. So, these are the answers. We went over this in class, revealed them at least, so I think that you should be able to know know how to do these now. All right, now, the other way, right, if I say that the pH is 2.8, for example, and I want to know what is the molar concentration of the hydrogen ion So what's the hydrogen ion concentration in molarity, right? So to do that in our calculator, right, we're going to take, so let's clear this up here. We're going to take pH 2.8 So we're going to say, you can do it a couple ways. You can just write 10 to the, and then you say a negative 2.8, right? And that would give us our value. So there's our molar concentration. You can also do second log, which provides the 10 to the, and then you write the negative 2.8. Okay, same thing. Okay, so if we have the pH, we take 10 to the negative, whatever the pH is, and then that will give us our hydrogen ion concentration. Molar hydrogen ion. Okay, very good. So then, let's take a look at this. pH. From the pH, you should be able to identify the hydrogen ion concentration. All right. Now the pOH, one more relationship that we did mention in class, but we can remind you of, is that the pH plus the pOH is equal to 14. Okay. So we see our pH is 2.33 plus whatever the pOH is will equal 14. All right, so with that information, you should be able to fill up this chart. Go ahead and push pause, finish it up, and then when you're done, start this up again. Okay, I'm going to go ahead. If you haven't finished, push pause and finish up. All right, so hopefully those are the values that you got. If you can't get those, go back and look at what I did with my calculator to make sure you can see what to do. Okay, here's a good solution, a good question. Push pause, answer it. All right, hopefully you have it answered. Moving forward. Okay, so ionization of strong acids is 100%, or dissociation of strong acids is 100%, right? Okay, weak acids, right, dissociate to a lesser percentage, right? And we're talking about now how we can identify the degree of dissociation based on the Ka of that acid, the K, the equilibrium expression for that acid. Now, because the dissociation of acids is 100%, when we say we have 0.1 molar HCl, like in this problem here, it also tells us the relative concentration of the hydrogen ion. So if I have 0.1 molar HCl, that's the same as having 0.1 molar hydrogen ion, and chloride ion for that matter, right? Because this dissociates completely into hydrogen ion and chloride ion, right? So if I have 0.1 molar HCl, I also have 0.1 molar hydrogen ion. If I take the negative log of my 0.1, then that will give me the pH of my solution. Okay, so do that. Make sure you get the right answer. Okay, moving forward, make sure you get it. Pause it if you haven't. All right, so the value is pH negative log 1. Now here's an ice table, which is kind of a little overboard. If it's a strong acid, you know what happens to the at equilibrium, right? But it sets us up for a weak acid, right? So strong bases also dissociate 100%. So if I know that I have a 0.5 molar calcium hydroxide, what is the pH of that solution? All right. So I'm going to look at this problem, see that I have 0.5 molar calcium hydroxide. If that dissociates completely, think about what the concentration of the hydroxide ion is going to be. Take the negative log of that hydroxide ion concentration, and that will be not the pH, but the pOH, and then the relationship between the pH and the pOH we already talked about, so you should be able to identify what the pH is. Okay? If you didn't get that, move back a few seconds, listen to that again, see if you can figure out what needs to happen, give it a shot, see if you get some answers, write it down, and then check your answers after you've pushed pause and gone through the problem. Okay, hopefully you got through the problem. Now I'm going to show you the answers, so make sure you work through it all the way. All right, so the pH of the solution is going to be 14. All right, now some people might have gotten a pH of 13, right? Or no, sorry. Some people might have gotten a different pH. For example, let's see, what would have been? Some people might have forgotten that when you take calcium hydroxide and you dissociate it, you get 2 moles of the hydroxide ion, right? 2 moles of the hydroxide ion. So although it's 0.5 molar calcium hydroxide, it's going to end up being 1 molar hydroxide ion. All right? So if I take the negative log of the 1, which is the hydroxide ion concentration, that will give me the POH. And then 14 minus the POH should equal the pH. All right? So if you had not recognized that it was 1 molar and you just took the 0.5, right? So you take the negative log of 0.5. Let's see. Then that would be the POH, and then 14 minus that. So you might have got a pH of 13.7 instead of 14 if you only took the 0.5 molar hydroxide ion. Okay, next. See if you can figure this one out. Same way, what's the pH? 0.5 molar solution of sodium hydroxide. Should be pretty straightforward. It's almost like we've already done this one. All right, take a few seconds. Try to solve it. Okay, if you haven't solved it by now, push pause. I'm going to move forward. Okay, so the value is 13.7, right? That's the one we just did where we pretended like, or for people who might have thought that 0.5 molar, 0.5 molar calcium hydroxide would result in only 0.5 molar hydroxide ion, right? Here we actually have 0.5 molar hydroxide ion, so the pH is only 13.7. All right, so that's the end of our chapter there, and now we're going to look more into the equilibrium of acids, of weak acids. All right, so chapter 17, we delve deeper into weak acids and also weak bases, or bases in general, utilizing their Ka to learn more about how strong the acids are, and also we can predict the pH of any concentration of a weak acid if we know the Ka. All right, so first of all, a little bit of a kind of a review, but to make sure we're all on the same page. We have a acid, some chemical, right, which is going to dissociate. All right, now this is the textbook way of writing it, but we can simplify it just a little bit, recognizing that this acid is going to dissociate into ions, right, Ha going to H plus and A minus, and that the K, the equilibrium expression here, is going to be the concentration of H plus at equilibrium times the concentration of A minus at equilibrium over the concentration of the dissociated acid at equilibrium. Okay, nothing surprising there. We've also talked about how this is called a Ka, right? Oh, sorry, just an A there. Why is it called a Ka? Well, that A stands for this chemical acting as an acid. All right, now you don't have to get too worked up about it. You just know that there's a K, and then you know the equilibrium of whatever this reaction is. And I should add in our second arrow here. Okay, so one thing that we have only mentioned for the case of water is that it is helpful, and we'll talk about how it's helpful, to express the equilibrium constant not just as a K, but as a pKa. All right, not just as a Ka, but as a pKa. And that means to take the negative log of this concentration, or this statement, right? Negative log of this statement. All right, if you take the negative log of it, then something interesting happens. All right, it gives you a pH. It gives you a value, a pH. And it's a special pH that pertains only to whatever the chemical reaction that you were talking about. And it's the pH at which exactly half of the original material will be in the dissociated form. Okay? And it becomes a very valuable tool. And we call that the pKa, right? So what essentially it is the negative log of this value, whatever this relationship is, which is at equilibrium. And then that pKa now is the pH at which 50% of the original reactant is in the product form. And thus, 50% of the original reactant is still as the original reactant. So half of these have dissociated when you are at that special pH. Okay? All right, so we'll show how we use that in a bit. First, let's talk about Kb. Kb, basically the same thing as Ka, but it's referring to a scenario where a chemical is acting as a base. So we have a nice equation here. This chemical acting as a base, right? A weak base, double arrows, right? So our Kb value, or our K for this reaction, is again just the concentration of the products over the concentration of the reactants. All right. Now, pKb can be taken, again, negative log of Kb, and the pKb will be the pH at which, again, half of our original material is dissociated. All right. So let's get in a little bit deeper to this Ka, or this pKa and this pKb. So here's our example, HA dissociating. It's a weak acid, let's say, so it doesn't completely dissociate. All right. If you were to alter the pH of this solution, so let me draw a container here so we kind of have an idea what we're talking about. Here's a container. It's water, all right? And we put some acid, HA, into this water, all right? And because we do that, the pH is going to change. But if we adjusted the pH of this solution by adding, like, let's say, a strong acid, which would donate just H plus ions. If we adjusted the pH of this solution by adding hydrogen ions, then that would be like adding a product here, and it would shift the equilibrium. It would shift the equilibrium one direction. Okay? So, the pKa then is essentially the amount of hydrogen ion that needs to be present so that 50% of this stuff is dissociated, right? Or in other words, 50% is dissociated in this form, the HA separated form, and the other half is in the HA associated form. Okay? And the same thing for the base, because the base equilibrium with water, right, has to do with, is dependent on the hydroxide ion concentration. You can see the equilibrium expression here contains the hydroxide ion concentration. And that hydroxide ion concentration will change if you add hydroxide ion, obviously, but also if you just add hydrogen ion. Because when you add hydrogen ion, it shifts this equilibrium, right? Which is the Kw for water. Sorry. Okay, so we talked about how Kw will always be a constant value, the amount of water that dissociates, and that if you add any hydrogen ion, then the hydroxide ion concentration will decrease, right? Again, pure water, here's a container of just water, nothing else, then the amount of dissociation from just water will be such that the concentration of these will be equal, right? And that's why we say pH of water is 7. And that's why Kw is 1 times 10 to the minus 14. Okay? So we have our Ka, which is this equilibrium's expression, right? Ka. And the negative log of it, or the pKa, is the pH that you'll need to have to make half of this stuff dissociated. pKb is a special pH for whatever reaction you're talking about to make half of this base proceed to products like that. Okay? So, take a look at this one. See if you can figure out what the answer for this question would be. Which of the following is a product in the acid ionization of H2CO3, carbonic acid? So, see if you can solve it. Push pause if you need to. I'll solve it now, so if you haven't solved it and you want to take a chance to do so, it would be good. Push pause. So, here we go. H2CO3 is supposedly behaving as an what? An acid in its ionization. All right, so if it's going to ionize, H plus is one of the products, and then it looks like we have HCO3, and that's going to have a minus charge, right? So which one is not going to be a product of the ionization? Well, if we further ionize this to, if you took this thing right here and ionized it into HCO3 minus, right, to H plus and CO3 2 minus, then you could get the CO3 2 minus. But for a single ionization, you're not going to get the CO3 2 minus. So our answer is just that one. That one is a product of this material acting as an acid. Okay? So, next. We also talked about the strength of a conjugate base of a strong acid, or the strength of the conjugate base of a weak acid. And we said that if the acid is strong, its conjugate base will not be a very good base, or vice versa. If the acid is weak, then its conjugate base will actually be a pretty good base, a strong base. All right? And that's true. Another thing that is true is that there's a relationship between the Ka, for a chemical behaving as its acid, and a Kb, or the conjugate base behaving as a base. All right? And that is that the Ka times the Kb will equal Kw. Or another way of thinking about that, the pKa plus the pKb will equal pKw. All right, so let me write that second one down. The first one's written down right up here already, right? Ka times Kb equals Kw. But also pKa plus pKb will equal pKw. pKw is 14, so the pKa plus pKb lazy on my K's. Remember, these are big K's. All right, is 14. So, what's the value of Kb for the following weak conjugate bases? All right, so if we have NAF and we want to look at the conjugate base, so what is the conjugate base here? Well, let's see. If Na was going to behave as a base, it would have to take a hydrogen from water and form NaH and result in the hydroxide ion. The other option is F interacting with water to take, so now this is actually not going to happen, right? Sorry, one thing that I forgot to mention there is that when Na takes that proton, it's going to have a +2 charge, right? Because it already has a plus charge. The other possible material in that compound, sodium fluoride, that could behave as a base is the F minus, and it would have to take a proton and form HF and the hydroxide ion. So these are the possible things that could happen to make, or so that one of the components in sodium fluoride behaves as a base. So which one do you think is going to happen? Well, this sodium ion has a plus charge. It's not going to want to take a hydrogen another plus charge, right? If sodium ion is going to interact with water at all, I mean, it would be taking a hydroxide ion, maybe. But this is not going to happen because this material is not going to form. However, F minus is the conjugate base of a weak acid. And we said that the conjugate base of a weak acid would actually be a fairly good base. So when F minus has the opportunity to pull a proton off water and form HF, that's going to happen. There's going to be an equilibrium associated with it, and the result is going to be the hydroxide ion. Okay? So we have to know then the Ka for this HF. If we know the Ka, for example, 6.8 times 10 to the minus 4. If we know the Ka, and that's the Ka for this HF, right? Then the Kb for the conjugate base will be, right? Back up to this, I'll rewrite it here. Ka times Kb equals Kw. All right? So Ka times Kb will equal 1.0 times 10 to the minus 14, which is Kw. All right, so there's a way that we will be able to solve for the Kb, and again, it's the Kb of the conjugate base of that acid. All right, so 1.5 times 10 to the minus 11, that's what we should get if we take 1.0 times 10 to the minus 14 and divide it by 6.8 times 10 to the minus 4. All right, another one. So what is the conjugate, or what's the Kb for the conjugate base of HCN? All right, so take a moment, review what we just did for the first one if you need to, and then try to answer this one here, the second one here, and when you're done, go ahead and push pause, start it up again, but for now, push pause and try to solve this one. Okay, hopefully you solved it and got the right value. All right, so same thing. If we have the Ka for an acid, or sorry, if we have a Kb for a base here, NH3, and we're looking at NH4 acting as an acid, this same relationship applies, and we can solve for the Kas for our acids. All right, you can look over that one if you want to a little bit more, but it's the same thing that we did on the other slide, but instead of giving the Ka, we're giving the Kb this time. All right, so here's a Ka for benzoic acid. What's the Kb for sodium benzoate? That, again, is the conjugate base for this, and we're going to solve this the same way. So go ahead and solve that one really quick. All right, we're going to move through it now. Hopefully you've solved it. Push pause if you need more time. Okay, so we can now, understanding this relationships, we can identify what the pH of a solution of a weak acid would be. Now let me remind you that if I said I had a solution of HCl that was 0.01 molar, 0.01 molar HCl, there's a container that has that much acid in it, and I wanted to know its pH, we should be able to do that now. Right? We should be able to know the pH of this solution. That's 0.01 molar HCl. Because strong acid completely dissociates. This means that 0.01 molar HCl solution means that it's also 0.01 molar H plus ion. Right? And 0.01 molar H plus ion, we take the negative log of that, and that would give us our pH, which in this case is going to be 2. And you can practice that, negative log of 0.01. make sure that that's the right answer, or that you get the right answer. Okay? But if I said I had a 0.01 molar solution of HC2H3O2, which is acetic acid, right? I have a different acid. It's a weak acid. Not all of it dissociates. Some of it dissociates into its ions. Oops. Some of it dissociates, but not all of it dissociates. So, can we solve for the pH? Well, it's not as simple, but yes, it's very doable. And in fact, after I show you, you're going to say, yep, I can do that, because it becomes simple. It does involve, though, an ice table. An ice table. It's solving for X. So, here we go. Here's my 0.1 molar solution of this weak acid, acetic acid. All right? The thing I need to know is I need to know the Ka for this acid, which is essentially telling me about the equilibrium concentrations of all the reactants and the products. Now let's remind ourselves. Let me see if we have it here. There's the equation that we're thinking of, right? This thing acting as an acid, so dissociating, leaving behind a proton, and the acetate ion, right? So we have to remember that that K is this thing acting at dissociating, and it's the equilibrium expression, equilibrium value, as an acid. So 0.1 molar means that that was the concentration of this acid that I put in there. So I can put in here my initial concentration of 0.1. Now, they don't say anything about having any products, so I just start off with 0.1 molar. Okay? The change. What is the change? Well, it's going to shift to the right. If there's no product, the reaction has to shift to the right. Okay? So, that means that this change here is going to be losing some, a minus X, whereas these ones over here are going to be gaining X. Now, this water one really doesn't matter, so we can just ignore it. But then the equilibrium concentration is just going to be the 0.1 minus X, and then these equilibrium concentrations are going to be 0 plus X and 0 plus X. All right, so then we can take our equilibrium concentrations. So disregard this 0.1 for now. We'll remind ourselves of that in a bit. But let's just write our equilibrium concentration, 1.8 times 10 to the minus 5. That's supposed to be equal to the concentration of the H3O plus ion, right, times the concentration of the acetate ion over the concentration of the acid associated together. Not dissociated, but associated together. And this is supposed to equal those equilibrium concentrations, which we see we can express the concentration of this as X, right? That's what this is showing us down here. We can also express the concentration of this acetate ion as X. And we can express the concentration of our acetic acid as 0.1 minus X. Okay? And then we could solve for that by setting it equal to 1.8 times 10 to the minus 5, which is the equilibrium constant for this expression. So, the situation here, though, is a little bit uncomfortable, right? And we talked about this before in a couple other classes, where if you solve for this, you're going to get X squared equaling 1.8 times 10 to the minus 5 times 0.1 minus 1.8 times 10 to the minus 5x, right? We have to distribute this through, and it gives us a polynomial, which we can solve with either our solver, right? Or we can solve with the quadratic equation. But we've also learned that this shift, right, which is this shift here, this change, that change, x, is going to be in the same ballpark or within a couple orders of magnitude of this shift. So maybe it's just going to be as high as 1.8 times 10 to the minus 3. But It's not going to be much higher than that. Therefore, because that shift is still so small compared to our initial concentration of 0.1, it's not going to be influential. And we can drop it from this problem here, leaving us with just x squared over 0.1 being equal to 1.8 times 10 to the minus 5. If I solve for x this way, I can put that into my calculator, 1.8 times 10 to the minus 5 times 0.1, and then I can take the square root of it, and I'll get a value of 0.00134. Now, what is that? That's my x, that's my shift, right? That is also the final concentration of the hydrogen ion. If that's the final concentration of the hydrogen ion, if I take the negative log of that value, that should be then my pH. So I'm getting a pH of 2.87. Okay? So, again, we simplified this by eliminating that x term because, excuse me, because I saw that the initial concentration of this stuff was so much higher than the actual Ka, therefore it wasn't, the shift here wasn't going to make a huge difference. All right, so another one. If I have a 0.1 molar solution of HCN, and here's our Ka, all right, see if you can set up the equation that the Ka represents for that compound, and then set up the ice table with the initial concentration, set up the change, set up the equilibrium concentrations, all right, put them into the equilibrium expression, which should be equal to 6.2 times 10 minus 10, and see if you can find out what the pH of this solution will be. All right, push pause now, finish it up. Don't cheat yourself. All right, hopefully you had a chance to finish it. Very similar ice table, right? 0.1 is our initial concentration, 0 B to the right. So we're going to lose some of this, and we're going to gain some of these two. All right, let's see, did we lose the camera here? Camera stopped working. All right, so we lost the camera for a while. Maybe it'll come back, maybe it won't. So then we have 0.1 minus x, which we can simplify to 0.1 because, again, this is small. So we can say that x squared over 0.1, which is our initial concentration, will equal our Ka value. Okay, so we should get a pH of 5.1. Hopefully you got that. All right, so we can do the same thing now for bases. All right, so here's a compound. It's 0.1 molar in concentration, and we want to determine the pH of that compound. We need the Kb because that's going to tell us the degree of dissociation, and we're going to need to make an ice table. All right, let me give you a shot to do this one by yourself. Think now, the only difference here is that N2H4 is not behaving as an acid. It's behaving as a base, and that's why they're giving you the Kb. Therefore, you need to write the expression N2H4, it behaving like a base. So the ice table is going to be exactly the same pretty much, except for the equation at the top is going to be N2H4 behaving as a base. So let's see if you can write N2H4 behaving as a base. All right, go ahead and do that. Go ahead and finish this one up as well. Push pause if you need to, and then finish this one up. Okay, so hopefully you could identify that N2H4 to behave like a base would have to interact with water, produce the hydroxide ion, and yield that compound, pulling a proton off of water. That's what bases would do, right? Initial concentration, 0.1, 0, and 0. Change, plus x and minus x. Sorry, minus x, shifting to the right, plus x. And then equilibrium concentration, 0.1 minus x. This is very small again, so it's just going to be 0.1 essentially. And then x and x. So our concentration of X, or our X value here, is going to be able to be solved to be 4.12 times 10 to the minus 4. Now, this is slightly different because we've now identified X, but that is not the hydrogen ion concentration. So I can't take the negative log of that and find out what the pH is. I can take the negative log of this value, but it would give me the negative log of the hydroxide ion is the pOH. And that's not far from the pH. 14 minus the pOH would be the pH. So if you didn't remember to do that part, go ahead and finish up here right now and find out what the actual pH would be, not the pOH. I mean, you can find the pOH first, but you want to get the pH eventually because that's what the question was asking. All right, hopefully you pushed pause and did that. If not, do it now. And let's see if you get the pH of 10.62. All right, same thing. Go ahead and finish up this problem as well, the bottom one here. 0.1 molar solution of ammonia. Kb is 1.8 times 10 to the minus 5. Set up your ice table. Push pause, fill it all in. Remember that you're solving for the pOH, or that the pOH, the X is the H, the hydroxide ion concentration, right? So if you take the negative log of that, it makes the pOH. All right, see if you can do it. Okay, hopefully you worked through it. And let's see, our pH is 11.13. Now, on a problem, on an exam, for example, if they say something like, what's the pH of this solution of weak acid? Or what's the pH of this solution of weak base? If they tell you it's a weak acid, then you should know that the pH of the solution is going to be lower than 7. So if you have some answers, or if you are in a hurry and you don't realize that, for example, for the identifying the solution, or the pH of a solution of weak base, if you don't realize that you've actually solved for the pOH and you see that the value that you're looking for is less than 7, that should make some bells go off in your head. Wait a second. This is a weak base. There's no way that the pH would be less than 7. And so then that'll allow you to review and recognize that you have actually identified the pOH, right? Okay. All right. So, what is the... Let's fix this a little bit more. Okay. So, what is the pH of a 0.3 molar solution of phenol? All right. This is a chemical, C6H5OH. We haven't talked about it much. That's okay. It's the kind of question where you get, you don't know exactly what to do with it, but you see that we're given a what? A Ka. So now we know that the C6H5OH is going to act as an acid, and that is the Ka for that equilibrium that will be attained as that material, phenol, behaves as an acid. Okay, so identify the concentration of hydroxide ion, which will be the X that you'd solve for according to the last couple slides. Take the negative log of that, and that should be the pH. So go ahead and finish this one up. Hopefully, if you've done it now, we're going to move forward. All right, so 5.2. 5.2 is the pH. Okay? And again, we knew it wasn't 9.2. We knew it wasn't 9.4 because those are basic pHs. Now, 0.52, I mean, you're not terribly familiar maybe with the relationship between the pH scale, but 0.52 is an extremely acidic condition. All right. Another question that is related to this is percent ionization. Percent ionization. Now, the K is an equilibrium expression that shows you the relationship between the degree of dissociation and the association. But percent ionization is something a little more easy for us to kind of visualize, right? If I told you that a Ka was 1.7 times 10 to the minus 4, you would have a general idea that the relationship between the reactants and products, because of the size of the number, right? But if I told you that only 0.1% of the reactant was actually dissociated, then that's a little bit more of a number that kind of we're familiar with. Okay? So percent ionization is just the moles of the material that's ionized relative to the moles of material that's not. Or no, sorry. Relative to the moles of total. moles total. So we would like to know the percent ionization of a 0.2 molar solution of acetic acid. Right? We're going to solve this problem exactly the same way as we did before. Right? We're going to, with the Ka, set up an ice table, set up our initial concentrations, the change in equilibrium, right? And then we're going to get rid of that X. It's not going to influence. Okay, looks like I lost the camera again. All right, after we get to this point here, we can set this value equal to our equilibrium expression, as we did before, solve for X. And now we have X value. Okay, so the X value that we've solved for here is the hydrogen ion concentration, but they're not asking for the pH, they're asking for percent ionization. All right, well, I know I started with 0.2 molar of the stuff, and now this is how much of this there is, or it's also how much this there is, which is the same, same value, X. Therefore, I can figure out how much has actually ionized by saying 0.2 was how much could have ionized if it were to go 100%, but this is how much that it actually ionized. So if I just put 0.19 times 10 to the minus 3 over, 0.19 times 10 to the minus 3 over 0.2 times 100, and then it'll give me my percent ionization, my X over my 0.2 times 100. And that's the percent ionization that actually occurred. So less than 1% actually ionized for this solution of acetic acid. And that's interesting because acetic acid is actually a relatively strong weak acid. All right, so moving on to the next one. Could you determine the percent ionization for a 0.1 molar solution of acetic acid? Okay, so we just did this 0.2 molar acetic acid, and now we're going to do it for 0.1. And maybe make a little guess in your mind. What do you think? Is it going to be more, a higher percentage ionized, or a lower percentage ionized? All right, so go ahead and finish this one up. All right, this is the last one for the lecture, so if you finish this one up, you're done, but don't look until you finished it up, all right, and make a prediction about, again, more or less percentage ionized. Okay, here I'm going to show you the answer. So we prepare an ice table the same way. We put in the changes that are the same. We got 0.1 in here instead. We identify X as 1.34 times 10 to the minus 3. That is, how does that compare? It's a lower value, 1.3 times 10 to the minus 3. This is 1.9 times 10 to the minus 3, right? Oh, sorry, that's let's see, did I say that right? 1.9 times 10 to the minus 3, and this one was 1.3 times 10 to the minus 3. So it's a lower percentage of amount in this ionized form. However, it ends up being a higher percentage ionized, right? There's half as much, so that's why you end up with a lower amount actually in the ionized form, but it's higher percentage-wise. And essentially, the reasoning behind that is because when you have a lower concentration, then you have more water molecules per molecule of acetic acid needing to be ionized, and there's less of the acetate ion floating around, therefore the equilibrium, again, would push towards the right. All right, good. I hope you learned a few things, and I will see you guys on Monday.